Okay, welcome back. This is still lecture 4. So you either are already happy with limits and colimits, or you just watched the previous segment and now you are happy with limits and colimits. Either way, sorry, initial and terminal objects, I misspoke. Either way, one way or another you're happy with initial and terminal objects, and now we shall define limits and colimits. Actually, we'll just start with limits. So colimits are going to be what you'd get if you take limits and then you change all the direction of the arrows when you work in the opposite category. We'll talk about those in more detail in the next section. But I want to go sort of slowly through limits to start with. So I'm going to give a definition which is completely equivalent to the one in Lenny Talman's notes, but is of a very slightly different, it's going to be phrased slightly differently. I guess you can read also the one in his notes and decide which one you find clearer. Okay, so let's see the category. Okay, so we're going to be taking our limits in the category C. Again, if you're looking for a good example of a C, you could take set, or you could take the category of topological spaces, or you could take groups, or something like that. And then let I be another category, say a small category, let's just say a category, which, I'm sorry, so I've just got two categories, but they're going to play very different roles. So this is the category in which we'll take the limit. This is called the shape category. Okay, and then a diagram of shape I is just a functor from I to C. Okay, this might seem strange language, so let's give an example. We could take something like C to be the category of sets, and then I can be any category, but a lot of interesting examples, this category I is very small. It might just have like 3 objects. And now, so if you have a category with very few objects like this, it's often helpful to represent it in the way that came up in lecture 1. You just draw the objects as dots and you draw the morphisms as arrows, but you generally skip out the identities and some composites to make the diagram look reasonable. So a category I might have just 3 objects, which we might call 1, 2, and 3. And then maybe the morphisms, there's a morphism from 1 to 3, and a single morphism from 2 to 3. There's also the identities, but following the convention, we're not going to draw this. And this is the whole of my category I. Okay, and so a diagram of shape I, it's a functor from I to C. So in other words, for every object of I, it picks out an object of C, and also for every morphism of I, it picks out a morphism of C between the relevant things. So with this example of C and I, a diagram of shape I is exactly the same as to give 3 sets, say, I don't know, S1, S2, and S3, these are all sets, and maps of sets between them. Okay, so hopefully this makes the terminology seem sort of reasonable. To give a functor from this I to the C is really the same as to draw a diagram of this shape. Okay. Of course, there's nothing particularly special about this shape. You could also choose any other category I. Okay, so given a diagram F of shape I, we have the notion of a cone 2F. Consists of an object. Sorry, I just want to check if I give it a special name. I'm going to call it N, an object of C, and maps, say, psi I from N to F of I for every I an object of I. Okay, so we're going to have our, let me get another color here. So maybe here is our N, and then for each of these, for each of 1, 2, and 3, we should have a map to, because remember S1 is just F of 1 by definition. Okay, so it's this guy N and this collection of arrows, and then So we're going to impose a condition, and our condition is that, in short, the obvious diagrams commute. So whenever I have an arrow between two objects in I, then I get a commuting triangle. I get a triangle like this in C, and I want to impose that that should commute. So such that. So let me get this correctly for all, say, G from I to J in my category I. We have that psi j is equal to G composed with psi I. Okay, so that's just saying that this triangle commutes and this triangle commutes, and that's it. Oh well, I guess if I do this and I do the identity, it's the same as doing this, but this is not much new. Okay, so this is a cone 2f. These are things like this. There might be lots of them. We want to now do a little bit better than just having the cones. We want to talk about a category of cones. So the objects are going to be cones to f. We need to have morphisms between them. So what's a morphism of cones going to be? Well, we're going to have a morphism, say, from n to n prime, as you'd expect. And then we're going to again impose some sort of compatibility, because we're going to have a bunch of new triangles, and we're going to insist that all of those commute as well. So let me write this down. So if, say, n and psi I. So this is one cone, and this is another cone, say m and phi I. This is a phi, I'm sorry. Are two cones over f. A morphism from to the m. Sorry, I'm going to be lazy and not write out all these index things again. So a morphism from here to here. It's just a map, say h from n to m. This is m and n objects of my category C, so this is, of course, a map in the category C, and such that, again, a bunch of triangles commute, such that for all objects of I, we have that psi I is equal to phi I composed with h. So let's just quickly draw it on our picture here. If this is my m, my other cone 2f, we're going to have a notion of cone from f later, so I'm emphasizing the 2 here. Okay, so a morphism of cones is just going to be a morphism from n to m. And then let's
put another color for that one, because that's different side.
Yeah, that's a good idea. Another color. Green, we have green. Okay, so it's this is my h from n to m, and then I'm going to require that for every object here, if I do this, it's the same as doing this and then this. Okay, and that's exactly what I'm capturing in this phrase here. Okay, so now we have ourselves the notion of a morphism of cones, and so this gives us a category of cones, and now we can define a limit. So definition, so a limit of f. Remember that f is our diagram of shape I, is a terminal object in the category of cones 2f. Okay, I've written, it's always a little tricky to decide whether to say a or the terminal object, because terminal objects are unique if they are unique up to unique isomorphism if they exist. But since they often don't exist, I think it's healthier to write a terminal object. So just as not every category has a terminal object, certainly not every diagram has a limit. But if there is a limit, then that limit is going to be unique up to unique isomorphism, which is very useful. So a good exercise for you is to read definition 8.23 of Lenny Tellman's notes, so CF 8.23, a precise reference is given in this type notes, which are available on the website, and check that the definition I've given is equivalent to the definition that he's given. So I've introduced this notion of cones to f, and I'm taking a terminal object. Lenny just writes out essentially the same conditions but without mentioning cones. So it's a good idea to check that you're really happy with the fact that these are the same thing. Okay, so that's the definition. Of course, it's rather abstract, so we need to see many examples. And I'm going to, I will actually come back to this example. So I'm going to give you several examples, inevitably not enough, though you can never really see too many examples of this kind of thing. Lenny's notes give a lot more examples, and I very much recommend that you go through the examples in his notes as well. So he actually starts by giving the examples and then the definition, which is an approach which has a lot of merit, but we're doing this the other way around, partly for reasons of time. Okay, but yeah, so I will give some examples, he gives many more. So let's first do a very silly, so I just want to sort of, to make sure that we've got our heads around the notation, I'm going to do a very silly example. So let's have our diagram. So C is any category, and I is going to have exactly two objects, and one, I'm going to call them, say, 1 and 2, and exactly one morphism between. And of course the identities on 1 and 2, but in fitting with our convention, we're not going to write these. Okay, so a diagram of shape I is just a morphism in C between two objects. So a diagram of shape I is just going to look like this. So this is I'm writing C1 to indicate that it's an object of C. This is just f of 1, and this is f of 2, and this is f of whatever the morphism between them is. Okay, and so here's our rather boring diagram of shape I. So what's a cone to it? So let's get some colors out again. So a cone to this thing is just going to consist of my guy n up here, and then arrows like this. And if I have a, okay, and then a morphism of cones is what it is. Maybe it's not so instructive to write this thing out again. Okay, and so, well, maybe it is. Here's my m. And then I have my nice green arrow between them. So cones 2f are going to look like this thing, and then I want to look at what's the terminal object in the category of these things. And the answer is very simple. The terminal object, I'm going to write it down here, is just C1 together with this map and the identity here. Okay, this is a very boring cone, but notice that every cone here comes together with a map to C1. So every cone admits a map to this sort of terminal cone, and the map is clearly unique, and that's exactly what we needed. So that's exactly what we wanted to say, that this is the terminal object.
Well, that's because in this case the column is completely determined by the map from n to C1.
Yes.
And in fact the same thing holds true if I as an initial object, same argument.
So if I...
If I as an initial object, then
Yep,
the same
indeed.
argument holds.
Yes.
So it could be
So I will
say
come-
a
yes.
straight line, or it's more
Yep.
complicated with an initial object.
Yeah. So what Rob is saying is that this is a special case of a more general phenomenon, which is that if your shape category I has an initial object, then every diagram of shape I has a limit, and that limit is just essentially f of the initial object. Okay, great. So there is a limit, but it's not so exciting. So now let's do a sort of more reasonable example. Let's do an example of products. Okay, so again, let C be a category, and that our shape category is going to be discrete. So what do I mean by a discrete category? I mean a category where the only morphisms are the identities. So you can also talk about categories where the only morphisms are isomorphisms, but that's a very different thing, and I mean much more interesting thing, let's be clear. So in a discrete category, really the only morphisms are the identities, so it's quite a boring thing. It could, of course, be finite or infinite. I'm not going to specify that just yet. So what's a diagram of shape I? So a diagram of shape I, to give a diagram of shape I, is exactly to specify an object for every object in I. You don't have to do anything with the morphisms. The only morphisms here are the identities, and by definition of a functor, they must be sent to the identities. So to give a diagram of shape I is just to give a collection of objects indexed by I. So a diagram of shape I is just the same thing as, say, a collection of like Ci for I in the objects of I. So, and then we define the product of the Ci's here to be the limit of this diagram. So in the complete generality, in any category, I can define the product of some of any collection of elements to be the limit of the sort of boring diagram which just sends a discrete category, one object to each of these elements. Okay, so why is this a reasonable definition? So the main motivation is that in some familiar category like set, category of sets where you already know what products should look like, this definition recovers the usual definition. So let's think about that, let's explain that a little bit. So I guess this is example squared, an example of the example. So C is a category of sets. And let's even make things easier. I just has two elements. Yeah, I could call them 1 and 2. Okay. And then, so our f of I is just a diagram, two objects, no morphisms between them. So say Si. I'm going to call them Si for set. Maybe that's reasonable. So I'll define Si to be f of I. And then my claim is that, so you know how to take products of sets, it's just the Cartesian product, pairs of elements. My claim is that this thing is essentially the limit of this diagram, of this boring diagram. Of course, remember that this is sort of, I haven't said this precisely enough yet. Remember that a limit of a diagram is actually a cone, it's not just an object. So the limit of the diagram is not only the C1, but it's also these arrows here. In general, a limit of a diagram, like, you have to specify the arrows in the cone as well. So I should do that first. So I have a cone to F, and that's going to be S1 cross S2 is my object. And then I should give a map to S1, and this is just a projection onto the first factor. And I should give a map to S2, which is the projection onto the second factor. So my claim is first that this is a cone to F. Well, there's essentially nothing to check here, because it's an object together with a morphism to each of these things, and all the triangles should commute, but there are no triangles to check, so there's nothing to be said. So this certainly is a cone to F, and the claim is that, or an exercise for you, this cone is terminal, i.e. it is the limit. Okay, this is explained somewhat in the notes, but I don't think it's a sort of there isn't really very much, it's mostly a matter of getting your head around the notation, and then this will be clear. So I want to conclude this section on limits by giving one more example, or sort of class of examples, and that is equalizers and kernels.
But maybe it's worth saying that if you look at your definition and you look at, say, the definition of a product in a category, then it's really a reformulation of exactly the same thing.
Yes, indeed. So if you think of the product, I guess if you're thinking in the category of sets, you maybe think of the product as the Cartesian product of pairs of elements. But if you think of products if you've already met products in general categories with a universal property, then it's a very good idea to check that the definition given here is just the standard universal property for the product in any category. If you've met that before, then you should check that works. If not, then you can take this as the definition. Okay, So the last example, equalizers and kernels. Okay, so again, I'm going to take a rather small shape category. It's going to have now two objects and two non-identity morphisms. So I is going to be the following category. Since there are two arrows, maybe I should give them names. Maybe they're called A and B. Okay, so definition. So the limit, so let f be a diagram of shape I. I guess so at this point C is any category. So f is a diagram of shape I, in other words a functor from I to C. Then the limit of f, this is often written lim f, unsurprisingly, is called the equalizer of, I guess, f of A and f of B. So this is a general definition. If you've met equalizers before, then they've probably been defined with a universal property, and it's again a good idea to check that the universal property you've seen before is just a reformulation of the definition of the limit of f. If you've not seen equalizer before, that's okay. You can take this as the definition. But I do want to focus on a particular case, which is the case of kernels. So an example. So let's say that C is a category of groups. And let's suppose that F is a diagram of shape I. And that f of B, say, is the zero map. Between f of 1 and f of 2. And so my claim is then that the limit of this diagram is the kernel of f of A. So the final exercise. So show that limit of f is the kernel of f of A. Now the kernel of, so again, really, normally you may think of the kernel as just being a subgroup, but you should really think of it as being a cone. In this case, well, it's a subgroup of f of 1, so the arrow here is clear, and the arrow to here is just a composite with A, or equivalently with B, both of which are the zero map. Okay, so that's everything I want to say about limits. I will let Rob press the turn me off button.